Hey guys, welcome back to my channel. In the last video, we touched upon what a mixture of experts model is and how the router helps us to choose the top K experts. Today, we'll write some code to understand the mechanics of mixture of experts. Most of the hype is around natural language processing, so we'll try to take the road less taken and code a mixture of convolutional experts. We'll start by coding a gating block and then use it to build a routing block. We'll start by importing torch and Thop. Thop is a library which calculates the number of learnable parameters of a model. There are three things that we would want to import from torch. Torch itself, torch.nn as nn, and lastly torch.nn.functional as f. And then we will from Thop we will import profile and clever format. A gating block's responsibility is to choose top K experts out of the given n experts. The setting would look something like this. There would be an incoming tensor to the gating block. This would be the gating layer, and when we apply Softmax, it's supposed to output logits of the shape, batch size, comma, number of experts. So if there are 4 experts, it would output probabilities which would look something like this, right? And we would need to choose top K of them. If K would be 2, then these 2 logits would be the maximum, and if there are let's say 4 experts, then 0, 1, 2, 3, 1 in 3 experts would be selected for the tensor to pass through them. So now the tensor would go through them, and we would get their output, multiply them by these respective probabilities. Suppose the contribution would be x1, this would be x2. So we multiply this by x1, multiply this by x2, and then we sum it up. This would be a weighted sum, and then this is the outgoing tensor. One thing to keep in mind would be that in the Softmax output, essentially what we would do is we would kind of remove these 2 from the logits and then take Softmax of the remaining top K logits, right? So it's not a Softmax of the whole thing, but the Softmax of only top K logits. The next question that we need to ask ourselves is, what would be a good design for the gating block? It has to be a convolutional network because we are dealing with images. It should be lightweight and should be fast enough so that we do not spend too much of compute there, and yet should be complex enough so that it learns to route to the correct experts. Right? I guess we can choose to experiment with the design. How about a Resnet bottleneck kind of structure, maybe with some modifications? So how does that look? Suppose there's an incoming tensor of which has okay, not 64 but 256 spectral depth is our incoming tensor. Now the Resnet bottleneck has 3 convolution layers. The first one is a 1x1 pointwise convolution where we compress the 256 spectral depth to, let's say, 64. Basically it's dividing by 4. 256 integer division 4 is 64. So we compress it down to 64. Then we do a special convolution of size 3 by 3. The spatial depth remains 64, and then we just sort of scale it back up to 256 using again 1 by 1 convolutions. The reason we do this upscaling is because there's a skip connection involved here, and you need to do that, and this would be your outgoing tensor. So we would be taking some inspiration from this design. So in our case as well, we do not want to spend a lot of compute on the gating layers, so we would make 2 changes to the Resnet bottleneck. Let me quickly draw it here. This is the incoming tensor. Let's assume its size is batch size comma channels C1. There would be some height and width along as well. So we would squeeze it using 1 by 1 convolutions to, let's say, C2, then do a 3 by 3 convolution, which would again result to C2 channels. Now here's the first difference. We do not go back to the C1 channels, but we would do a 1 by 1 convolution and go to number of experts, number of channels. So the number of channels in the last layer would equal to number of experts, 1 channel for each expert, right? And we are going to ditch the residual connection as well. So this is going to be our outgoing tensor, where we would do the Topk thing and then the Softmax thing, right? So let's probably dive into some code. Let's write the code to make the understanding concrete. So I pasted the image that we just saw as a reference here and fixed the image size to be 2 to 4. Let's code up the GatingBlock, and then so let's call it GatingBlock and then dot module. So this is the constructor, and we would be having 3 inputs here: the C1, the C2, and the number of experts. So C1, C2, number of experts. It's usually good to have dropouts as well. It's good to have dropouts because they add regularization effects. So nn dot sequential, the first convolution would be a 1 by 1 convolution from C1 to C2. Kernel size would be 1, padding would be 0 because we do not want to change the image size. Let's have some batch term here, C2, then let's add some non-linearity, then add some dropout, 2D drop out, right? This is our first layer, the 1 by 1 to C2, and let's now code up the 3 by 3 to C2. Let's copy the block here to here. C2 to C2, kernel size is 3, padding would be 1 because we are using a 3 by 3 kernel. And now for the last part, where we are going to map to our number of experts. Incoming here is C2, then we map to number of experts. We thought we would be having a 1 by 1 convolution here for performance reasons, but since C2 and number of experts are if they are not a big number, then probably having a 3 by 3 kernel is also not a bad idea. But yeah, we'll stick with the 1 by 1 convolution, and maybe if you want you can experiment and let us know how that went. So in the forward function would be a very simple one. We just run the gating model and return everything, right? Okay, let's see whether this thing executes or not. So let's initialize a gating layer for us and see. C1 could be 32, C2 we can downscale to 8 for the time being. Number of experts, let's keep it 4 because that's what we have been doing till now. Copy this here and see. Yep, looks good. Let's try to see whether the forward function correctly executes the model or not. Let's give some dummy values to it. Torch.no grad gating output equals to gating, did I name it gating block, torch dot some random values, image size, comma, image size. I mean, these are just some dummy values just to see whether our model is executing or not. And yeah, we do get something. That's the shape. Okay, so the number of experts is 4, but we have, instead of a value, we have an image. So what we should do right now is do something to make this thing size 1 by 1. So instead of having bs comma number of experts comma height comma width, what we want is batch size comma number of experts, right? So this is because we want one number for each expert, and when we apply softmax we would want some probabilities for it, right? So that we know which expert to go to. And one good way to do that is to reduce this thing to size 1,1. This would be 1,1 essentially, but yeah. So a good idea is to do an average pooling on the spatial dimensions. That means taking average of the last 2 dimensions, right? So the way we do that is gating output equals to gating output dot mean 2, 3. So this is 2, this is 0, 1, 2 and 3, and we are taking mean on the last 2 dimensions. Now let's see dot shape. Yep, it's indeed 1, 4, and that's what we wanted, right? We can even go ahead and see what values do we have. So yeah, looks like this. So if we do a Topk on this tensor, looks like this would get removed and we would have this and this. Probably softmax would, I don't know, give like 60% the weightage to this and 40% to this. The above tensor gives importance weights for the 4 experts according to the gating block, where a higher number means more importance. Since we want to activate only top k experts, let's see which are those experts for k equals to 2. For that we can use PyTorch's Topk function. It returns 2 tensors, the first one being the actual Topk values, and the second tensor has the indices for those Topk values. Let's see. So gating output dot Topk, where k equals to 2, this would give us 2 values. This is the first one, values, where these are the top 2 tensors and these are the indices for that. So let's save them as Topk logits comma indices. And for so that we remember what each thing is, let's use this. These are called f strings, and these are one of my favorite things in Python. So it just says that if you put an equal to here within an f string, it will display its value along with the variable's name. Pretty neat. Now the values do look like Topk values, since the other smaller values are removed now, but it still doesn't show us the relative importance weight for each of the expert. Softmax can help us here. We just have to apply that in the last dimension. So the reason is that because if we take the shape of the tensor, it says 1 is the batch size, 2 is the number of experts that we have, the top k value. Right, so f dot softmax, we want to apply it on the top k logits on the last axis, and this is what we have. So it's look like almost equal weights for each of them. One thing to keep in mind is that the experts are not yet trained at all, and once they are trained, they would probably give some sort of slightly different values, slightly different weightage to each of the experts. Could be same, could be different. Right now these are just random values since our experts are not trained. Right, so let's call it relative importance and save it. Ideally the sum of it on the last axis should always be 1. Let's see, yeah, it's 1. Cool. So in the deployment setting, we would invoke only the expert number 0 and expert number 1, and expert number 2 and expert number 3 need not be disturbed. That's the whole point of having a mixture of experts model. You only invoke those experts which have the maximum probability according to the gating network. So I went ahead and put everything that we did till now into a class called router. It takes in channels, down channels, number of experts, and top k as parameters. These are nothing but the C1, C2 and the number of experts that we had, and it basically does the same thing that we just discussed. So just to see that it does the same, returns the relative importance and the IDs of the experts to run.